Good day. So today we're going to look at momentum and impulse. You might have heard these words before, like the word momentum. Momentum is defined as the product of an object's mass and its velocity. It is actually just thinking of it as mass in motion. Like, for example, a train that's moving has got a very high momentum because it's got a high mass, or a bullet has got high momentum as a result of its high velocity, right? How about a bullet train? That's something to think about. All right, linear momentum is looked at as a vector quantity with the same direction as the velocity of the object. That's what we call the linear momentum. But momentum in calculation is given the symbol P, small letter P, equal to mass multiplied by V, which is the velocity. So let's look at it. Mass in kilograms, okay? Velocity in meters per second. Let's think again. Kilograms, are they vectors? Are they scalar quantities? Mass is a scalar quantity. And velocity is a vector, right? When you multiply a scalar and a vector, what do you think you end up with? What is momentum? Is it a vector or a scalar quantity? You might need to refer to our workbook to also find out more about what happens when you multiply a scalar and a scalar, a vector and a scalar, and a vector and a vector. In this case, our momentum is a vector quantity. What's the vector nature of a quantity? The vector nature of a quantity is that a quantity will have magnitude as well as direction. That's what a vector is. Let's move on and dig deeper into momentum. I know at some point in time we talked about Newton's laws. And one interesting law that we use for calculation is Newton's second law. We can be able to express Newton's second law in terms of momentum. How do we do that? By stating that the net force acting on an object is equal to the rate of change in momentum. Each time you hear in physics, when you hear us talking about rates, it must make you think about change in time. And we are saying the rate of change of momentum is equal to the net force. In other words, the net force acting on an object is equal to the rate of change of the object in the direction of the net force. The rate of change of momentum of the object in the direction of the net force. So, for example, if we are going to move this object in that direction, the rate at which it is changing its velocity as a result of momentum gives us an idea of its net force. Well, let's break it down a little. This is a very interesting one. If we look at F net according to Newton's second law, it's equal to mass times acceleration. Basically, mass is just m, and acceleration is v, right? Final minus v initial divided by change in time. If you further expand this, v final minus m v initial, right, over change in time, what the top part gives you is m times v. If you go back, what's m times v? Momentum, right? So a change in momentum, rate of change in momentum relates to F net. So that's where we come up with Newton's second law in terms of momentum. Look at it again, think about it, you'll realize how it is very easy to come up with this concept. F net is equal to change in momentum divided by change in time. Now, we need to calculate the change in momentum when a resultant force acts on an object and its velocity, like, increases in direction of motion, e.g. the second stage of a rocket. The rocket goes, and then at the second stage, it loses part of its mass, and it begins to increase in velocity. So there is a change in momentum. Or when something decreases in velocity, it changes in momentum. Like, for example, when something is moving and brakes are applied, that is a decrease. Or when something is moving in one direction and then we change the direction, we have to think about how we can calculate the change in momentum. If momentum is a vector, we must be clear on the fact that our vector diagrams can be able to express or show the momentum and the change in momentum, which means we need to have an idea of direction, we have to have an idea of the size. Another very important concept that I need to introduce quickly is the concept of impulse. Impulse is the product of the net force and the contact time. Impact is the product of the net force and the contact time. Impulse is the product of the net force and the contact time. If you take the equation, for example, that we used before, right, that says F net is equal to change in P over change in T, and you transpose the change in P, bring it here, multiply by change in T both sides, you transpose the change in T, it will be change in time multiplied by F net is equal to change in P, others have it as F net times change in T is equal to change in P. It still is correct. Okay? This in itself is the quantity or the expression that shows what impulse is. It is actually the product of the net force acting on an object and the time that the net force acts on the object. This principle is very, very vital. The time that the net force is acting on the object. What are some of the applications of impulse? Applications of impulse could be in safety, where we got airbags. What do airbags do? When the car is involved in an accident, what happens? The airbag comes out. And so your change in impulse, your change in time, is going to be greater, which means the net force experienced by the individual will be less. It's also in seat belts and in arrestor beds. We can also apply it in sporting activities, where when you increase the contact time, between the ball and the racket, you actually increase the change in momentum. That should be easy and that should be clear. So those applications are very important. You must know them, you must understand them, and you must be able to remember them. Another very important aspect required in our calculations is conservation of momentum. When something is conserved, it means it's kept, right? We need to know these words. System. A system could be one or two things that are joined together or more, they form a system. We need to know this word external force, which is forces that are outside. Internal forces are forces inside, external forces are forces outside. Stating the law of conservation of momentum is simply as follows. The total linear momentum, I've defined the linear momentum earlier on, of an isolated system. An isolated system is a system where there are no external forces, okay, remains constant or is conserved. So what are we saying? We are saying if I am going to consider two or more objects, their total linear momentum is going to be the same. So the sum of the momentum of the object's initial is going to be equal to the sum of momentum after. Does that make sense? We'll break it down and show you a little bit further what we mean by this. When we talk about the sum of linear, this should be final, PF and PI being equal. So what we are simply saying is that if these two objects are of the same masses, right, and initially they are of velocity 0, their total linear momentum before I move them is going to be equal to the total momentum after I have moved them or after they are released. We'll look at questions that have to do with that in a moment. All right, like this question that is talking about two objects or two trolleys X and Y, right? It's talking about two objects X and Y, and it says that objects X and Y of masses M and 2M, all right, are compressed by a spring, right, between them. Initially, they are stationary, meaning they are not moving, on a horizontal floor, as shown below. Ignore the effects of friction. The spring is now released and falls to the ground while the trolleys move apart. The magnitude of the momentum of trolley X while it is moving away is, so we got these two trolleys that are moving away from each other. The other one is heavier than the other. The question is the magnitude of the momentum of trolley Y, X in this instance, the lighter one, is going to be, how does it compare? As I always say, when you get questions like this, it is important for you to make reference to a law of physics. Like in this instance, I would refer to the law of conservation of momentum. So, what is going to happen? I know that the final momentum is going to be equal to the initial momentum. The sum of the final momentum is going to be equal to the sum of the initial momentum. What do you think is going to happen if we got two bodies? Right? They are going to move in terms of direction, opposite, same direction. Which one will go further, the lighter one or the heavier one? Think about it. That is the clue to answering this question. So to help you out quickly, let's just talk about it. The magnitude of the momentum of trolley X while moving away is, so trolley X moves in that direction, trolley Y moves in that direction. The magnitude of that trolley's momentum, what I know for a fact according to Newton's, according to the law of conservation of momentum, is that the sum of the momentum initial is equal to the sum of the momentum final, right? Which means that, very important, let's have it clear now before it's late. There is space here, let's do it here quickly. Sum of initial momentum is equal to sum of final momentum. Okay, P initial is equal to P final. All right, now if they are going to be the same, these values of momentum, right? It means that the mass and velocity, right, initial of objects X plus the mass times velocity initial of object Y is going to be equal to mass times velocity final of object X plus mass times velocity final of object Y. What do I know about the initial momentum? The initial momentum is 0. Why is it 0? Because they are not moving. The question says they are stationary. They are at a standstill. They are at rest before, they are initially stationary, right? Before the spring has been released. Okay? So, what should I know about the momentum then of this one and that one? What are my answers? The momentum is 0? No. The sum of the momentum is 0, yes. Half the magnitude of the momentum doesn't sound right. Twice the magnitude of the momentum, it won't work out in this case. The same as the magnitude of the momentum of trolley Y. That is the correct answer, D. Correct answer will be, these momentum are going to be the same. But the only thing that's different about this momentum is their direction. Why would this give us 0? It's because they are moving in opposite directions, but their magnitudes are exactly the same. So it will be just m minus m, or we can put it as mv, all right, minus mv. This p will be the same value, all right, which gives us back the value of 0. This is a very important part of our understanding the aspects of momentum, and we'll come back to it in looking at questions that are to do with momentum, and impulse. Let's move on to yet another question and see what happens. Here is a question from 2015, and I'm just going to put in the details because I see the top part is not clear on the board. It says that a bullet of mass 20 grams is fired. So here is a bullet of mass 20 grams, right? Remember that in our calculation of momentum, our mass is always in kilograms, our velocity in meters per second. So when I see 20 grams already, I'm like, oh, I must change these grams to kilograms. Okay, so let me do it quickly. Is equal to 20 times 10 to the power negative 3 kilograms. Okay, just to be on the safe side. All right, so what is happening? It's fired from a stationary rifle of mass 3 kg. All right, and assume that the bullet moves horizontally immediately after being fired. The rifle recoils back with a velocity of 1.4 meters per second. So we got a rifle. I'm not an artist, I'm just a science teacher. Let me just try to draw a rifle here that has fired the bullets. Yeah, that looks like a rifle, doesn't it? Yes, it does. Okay, so the question then says calculate the speed at which the bullet leaves the rifle. What's going to be the first thing that must come to mind at this instant? At this instant, I must think, what am I going to use to come up with the answer? How am I going to calculate this particular question? Very easy. We are actually applying the conservation of momentum. Exactly that. So I said keep that in mind. Let's do it as quickly as we possibly can. So, can't use the red one, it won't be clear. So this is 4 points. 1 point, 4.1, all right? So I know you get a mark for this. The sum of initial momentum is equal to the sum of final momentum, right? Initially, what is happening? We know that the mass of the gun, let's call it the mass 1, plus the mass of the bullet, let's call it mass 2, times initial velocity, is going to be equal to the mass of the gun times final velocity of 1, the gun, right, plus mass times final velocity of number 2, all right? You can interchange them, it's still fine, it gives you the same thing, as long as you remember what you have used for the other one, all right? Now, what is it that we know in this particular instance? The question is clear in letting us know that initially, right, before firing, everything is at a standstill. So, the mass of the gun is 3 kgs, if I'm not mistaken, yes, plus the mass of the bullets, which we have now changed to kilograms, 20 times 10 to the power negative 3, multiplied by 0, is equal to the mass of the gun multiplied by the final velocity of the gun, which we don't know, plus the mass of the bullet raised to the power 3 multiplied by, do we have the final velocity? Oh, the final velocity of the gun is what we have, 1,4. So this one we have 1,4. We are looking for the speed at which the bullet is going to leave the gun. So on this part, we are looking at the bullets, the gun, and the gun. Simple equation we can solve now for F2, which is the final velocity of the gun. Pull out your calculator. Let's do the calculations. What are we looking at? We are looking at 3 plus 0,02 all multiplied by 0. Okay, and then we subtract 3. We add 3 times minus 1,4. Can I just take note that the bullet is leaving at an opposite direction from the gun. So if we are going to choose, right, forward to be positive, because remember vectors have got direction, so my velocity forward will be positive. Just make a change on that one. And my final answer is the velocity is equal to 210 meters per second. That is the velocity at which the gun, the bullet is going to leave the gun. Very simple. You can also choose the other direction to be positive, all right, which means that will be a positive, and so your answer here will be negative. Our final answer will be 210 meters per second to the right, okay? Or forward, or in the direction or opposite direction of the bullet. Now that's that answer for that question. Let's move on to the next part quickly. 4.2. 4.2 then simply says, calculate the magnitude of the average force exerted by the block on the bullet. What do we know about force? We know that the F net is equal to change in momentum divided by change in time, right? We have got that equation and that understanding that F net is equal to change in momentum over change in time, right? In the question, we have heard that do we have time in this question? All right, so we might have to find the time, the value of the time that the bullet has. That's very easy. We can find time, okay? We don't have the time here. Let's look for the time. According to the equations of motion, we know that we can find or calculate time by using V final is equal to V initial plus change in t. Acceleration times change in t, right? So let's look for the acceleration and then use this equation to find the value of the time. How am I going to find the acceleration? I need to find my acceleration there. So I would use V final squared is equal to, these equations are there on your book, at the back of every question paper, is equal to V initial squared, right? Plus 2A times change in x. Okay, so 0 is the initial, the V initial is 210 squared plus our acceleration, which we are looking for, 2a multiplied by the change in y, which is a distance of 0.4 meters. All right, all that information is given to us for use. Therefore, the value of acceleration in this instance of the bullet is minus 55,125 meters per second squared. You can do the calculation. I had done it prior to this. All right, so that's our acceleration. Let's substitute now the acceleration into this equation, where we are saying our V final is equal to V initial plus acceleration times change in t. What we are looking for basically is the value of the change in t. So our V final is 0. So if we say V final is equal to V initial plus A times change in t, so that's 0. The V initial 210 plus, all right, a value of minus 55,000 125 times change in t. Therefore, the value of change in t is 0,004 seconds. Okay, just be careful not to approximate it before the end. So keep the value without approximating. All right, now that we got change in t, our F net can be calculated by using this very simple equation that says change in momentum divided by change in time. So that will be change in momentum is mass, V final minus V initial, divided by change in time. Our mass, that is the mass of the bullet, is 20 times 10 to the power negative 3, which is, okay, I'll put it at 0.2 here. And the final velocity of that bullet was 0, and initial was 210, and we said our time is 0.04, giving us a force in newtons equal to, you can do it on your calculator, I did it prior to this for the sake of time, which is equal to 1,050 newtons. Go through the process, take a look at it step by step, and see if you can calculate it on your own. The final question says, how does the magnitude of the force calculated in the previous question compare to the magnitude of the force exerted on the bullet? Write down larger than, smaller than, or the same. What do you think? Newton's third law? It will be the same, equal. So for 4.3, the answer is equal. I know this lesson has been a roller coaster, but I want you to grasp the aspects of momentum and impulse. And I know we have picked up a few things from aspects of the equations of motion and we have amalgamated them with a question on that applies Newton's second law in terms of momentum. But this is an excellent way to fully understand Newton's law. There are other questions that you can look at, like, for example, a car of mass at 1,500 kgs, right? Okay, this question is not clear here. Let me just go back again and take a look at it on a clearer page. It says, the graph below shows the momentum of car A that changes with time just before and just after the collision. So this is just before and this is just after. And it's showing you momentum. So you got P. The first question say, what do you understand by an isolated system? You must be able to answer that question. Isolated system is a system where there are no external forces. The next part says, calculate the magnitude of the velocity of the car A just before the collision. So you know that momentum is equal to m multiplied by v. You know the value of the momentum before the collision. You know the mass of the car substituted there. You can find the value of the velocity. That's 3 marks. And the velocity of the car B just after the collision goes through the same process as we did here. Initial momentum is equal to final momentum. And do your working out and you would find the answer. This one says calculate the magnitude of the average force during the collision, right? So we are asked to find the average force during the collision. Do we have an idea of the time? Yes, we do. If we have the idea of the time, we can calculate average force by multiplying the mass of that vehicle times the change in velocity. This is how you would go about in your calculations, where we are putting together not only momentum, but also applying the second law of Newton in terms of momentum, also applying aspects of impulse and the law of conservation of momentum. Well done. This has been a roller coaster. Ciao from Chiefs.